Okay, so here's the last video that we're going to do for acids and bases. What we're looking at here is a comparison, right? So here we have three different titration curves. We have a weak acid with a strong base, a weak base with a strong acid, and then the one we did in the previous video, which is a strong acid versus a strong base. So take a minute and I want you guys to take a look at a few of the differences when you're comparing and contrasting these titration curves. One of the first things I want to point out here is take a look at the starting pH between a weak acid and a strong acid, right? In a weak acid, you can clearly see that we have a little bit higher of a pH for a starting point as compared to the strong acid, right? Another thing to pay attention to is look at the way that we see the increase in the amount of pH as we're adding solution. Now, remember, the x-axis still represents the amount of solution that's being added by milliliters, right? So that's still the same. But look at the difference in the curve. I mean, obviously, you have more space under the line, under the curve, in a weak acid. But take a look at the increase in the pH. You can see here that it's a little bit more subtle from here to here, right? It's not quite as smooth on the way up. The reason that happens is because this is what we call the buffer zone. And this exists when we're working with weak acids, right? The buffer zone is the part of the curve that you can clearly see that it's fighting a little bit more to change pH. And that's because in this area with a weak acid, it's actually acting as a buffer. And we'll get into why that happens in just a minute, but that's one noticeable difference. Now, the other noticeable difference is I want you to pay attention in the initial addition between the 0 and the 5 mLs of the base. Look at the dramatic increase that we have here in a weak acid, right? When we have a weak acid, we have a slightly faster jump in pH, and then we get to the buffer zone. So for example, here we jump from starting like say 2.5, right, to about almost 4, where here we go from a 1 to, a 0.75 to about a 1. So the increase in pH is a lot more dramatic when you have a weak acid compared to a strong acid. The bases are just the same. When you have a weak base and a strong acid, you have the dramatic decrease in pH, and then you reach what we call the buffer zone, which is this area here, and these guys experience the same thing. Again, we'll get into why that happens in just a minute, but just want you to take note of that. The other thing I want you to kind of pay attention to is I want you to take a look at the equivalence point area. So in the strong acid, strong base, we had the equivalence point happened at 25 mLs, right? We see the same phenomenon or the same amount happen at 25, right? Sorry. Okay. So, but I want you to pay attention to look at the amount or the increase that we see in a strong acid versus a strong base compared to what we see in a weak base or a weak acid with a strong base, right? So there is an increase in basicity or in pH, right? But you can see that the increase is not as dramatic. If you remember from the previous video, just adding, I think, the additional 0.01 milliliters of the base jumped up the pH, I think, by a level of 3. So you can see that it's not as dramatic in this situation compared to the strong acid and the strong base. And we'll get into that in just a minute. So in this buffer zone, right, just like before, we have that half equivalence point, which right here is going to be here, exactly where it was here, okay, at 12.5, because that's halfway from 0 to 25 where we begin to see. In this situation, it's exactly the same thing, right, where you have an area that the weak acid is the dominant species. We'll put the HQ here, right? This is the terminology they used in Google in AP Classroom. The HQ for the weak acid, and then here is the area where it begins to dominate and you have free salt, right? So what's happening in a weak acid is that it's reacting with the base, right? So it partially dissociates because it's a weak acid. It doesn't dissociate as much. And as it begins to neutralize, it's releasing an acetate ion. An acetate ion is an ion, is the anion of the acid that is released when it's combined with water, right? Now, this acetate ion, which is this one here, you take a look at the reaction, you can see that the acetate ion actually reforms to make this salt, right? So in the reaction, what happens is this acetate ion dissociates, right? Sodium and acetate go floating, and it acts as a Bronsted and Lowry base, and it's able to react with the water. So because it's able to react with the water, right, it's called it goes through the process called hydrolysis. Now, as this ion hydrolyzes, sorry, as this ion hydrolyzes, right, it begins to form the salt, and essentially it begins to act like a buffer. So we had our lecture about buffers and how they keep the pH from changing in small amounts, and that's exactly what's happening here. So if you remember, when we make a buffer, we have to use a strong acid and a weak acid to make that buffer. All right. Sorry, weak acid and weak base. Misspoke there for a second. But the reason that we use the weak acid and the weak base is because these ions are able to react with the water, and that causes the pH to change more slowly. Now, the question is, how do you know which acid is going, or which acids are going to have an anion that's going to hydrolyze with water? So that's very simple. I'm going to scroll up here to our past notes, and I want you to take a look at this list of acids and bases here. Okay, strong acids. Hydrochloric acid, hydroiodic acid, nitric acid, hydrobromic acid, and hydrochloric acid, right? Perchloric acid, perchloric acid. Okay, commit these acids to memory. All right, these are what we consider the strong acids. If it's a strong acid, it's not going to produce that free anion, right? It's not going to react with water. It's not going to hydrolyze. If it's not one of these acids, then it's going to do this, right? It's going to be a weak acid, and it's going to have that anion that reacts with the water, and it's going to do that. It's going to produce that buffer, okay? So again, take a second, commit these to memory, and if it's not one of these, right, then you're going to assume it's a weak acid. So let's go back down and let's take a look at our graphs, okay? All right, so here's where we're at, all right? These are the differences between the three types of titrations that we see, where you see that buffer zone, right? And then where you see the equivalence point. Now, the reason that the equivalence point matters is because it's going to come a point where you're going to get a question that's going to ask you which is the perfect or the best indicator for this type of titration. So what you're looking for, right, in an indicator, because you're going to get a question that's going to ask you, this indicator has this range, this indicator has this range, which would be the best one? So the perfect indicator would be right at the equivalence point. But remember that if you're within this zone here that we outlined earlier, right, if you're within this zone here, if you remember, it does not take a whole lot, right, for the acid or the base to jump in pH or decline in pH if you're within this range, right? I mean, you remember from here to here, it was a difference of 0.01 mLs that was added to achieve that huge jump. So if you're within that range, right, along the equivalence point, then you're going to choose the indicator that is going to be within that range, right? Now, for example, phenolphthalein, right, has a range of between right here, right, which is right around 8 to about 10, right? Now, in this area, right, there's not going to be a whole lot that's going to that you're going to have to add or change for that color change to happen. But you want to make sure that you're not getting an indicator that's too low, that's beyond the range of this area. For example, if you were to get it phenolphthalein would actually be a perfect one for this weak acid too, because if you can notice, the endpoint is, or yeah, the endpoint or the equivalence point is right within the range of your indicator, which would be a perfect endpoint. For this one, however, if you look over here with the weak base and the strong acid, then the indicator that would be better here would be the methyl orange, right? Because remember, you're adding in this direction. So what's happening is the pH is going in this direction. So you want to get something that's going to be at the end of your equivalence point and not something before. So even though, if you can take a look here, if you were to use phenolphthalein, phenolphthalein would have a range from here to about here, right? And that wouldn't work for you, right? Because you'd still be adding before you hit the endpoint. So the methyl orange in this situation would be the ideal indicator. So when you get questions about which indicator would be the best to use, remember that you want to use something that's going to be in the direction that you're adding, right? And it's going to be within this range here, right? To make sure that you hit either at or right after the endpoint, right? Or the equivalence point, sorry. All right. Okay. So here's the last thing that we're going to do. This is going to be a much shorter video. We're going to zoom in a little bit. And it says, based on this graph here, this is the one that we're working on, right? It says, calculate the pH of the resulting solution after 20 mils of 0.2 molar NaOH. Sorry, that was misspelled. Solution has been added to the 25 milliliters of the weak acid, which is the acetic acid, right? Okay. So this is where we're going to get into a little bit more detail about the buffer. Let's start with the amount of moles, right, present. So right here we have 25 mils of the acetic acid. Sorry. Okay. We all, of course, know that molarity is equal to moles over liters. So if I was to get this, this would be 0.025 liters. If I multiply that by its molarity, then I'm going to end up with 0.0050 moles of the acetic acid. This might look familiar because it's pretty much the same amounts that we've been using, okay? We're going to add 20 mLs of the base. So that's going to be 20 mLs of the NaOH. All right. And again, moles per over liters, we're going to say that this is 0.020 liters, sorry. And then we're going to multiply that by its molarity, which in this case is 0.20. Ooh, today's just not my day. Okay, and that's going to give us a total of 0.0040 moles. Okay, so this is the amount at this point, right, of NaOH has been added. So NaOH added. All right. Now, the NaOH is going to neutralize, right, the acetic acid. So we want to figure out exactly, what the pH is of the acetic acid or of the solution at this point, right? So it's going to be the same thing we did before, right? At this point, it's going to be 0.0050, right? This is moles of acetic acid. And then I'm going to subtract from that, right, the amount of moles that we added of the NaOH. Okay. So what's happening here, right, is if we take this and we take the difference, we're going to figure out that we have 0.0010 moles of acetic acid, right, that has been unreacted or unneutralized, right? This is unneutralized. Okay. Here's the difference between a weak acid and a strong acid. We've neutralized the 0.004 moles of acetic acid. But what that means is that 0.0 moles of acetic acid have released 0.0040 moles of acetate, right? The acetate is the anion. Remember, it's this one. Okay, so because we have this many moles of acetate now in solution, this is the one that's going to react with water, right? This is going to hydrolyze. All right, and what that means is it's going to accept those protons from the water. So it's going to be reacting with the water. And when that happens, it begins to act like a buffer, right? Because you have that weak acid and that weak base. So it begins to act as a buffer. So in order to calculate the pH at this point, then we have to use that Hasselbeck equation, the one that we learned the other day. And that one says that the pH of a solution, right, is equal to the pKa, right, plus the log of the anion over the acid, right? So we know that already. So here's how we calculate the pH. The pH is equal to the pKa, which we already know, right? For acetic acid, we did this before. It's 4.74, right? Plus the log of the amount of anion, in this case, is 0.04 over the amount of acid. This is the amount of acid still in solution that has not been neutralized, right? And that's going to be the 0.001, okay? As we simplify this, we're going to end up with 4.74, all right, plus 0.60. Therefore, we're going to get a pH of 5.34. Now, this is our pH of our solution, right, of that weak acid. Now, if we scroll up at 20 mLs, we're here, right? I want you to make sure you avoid the trap, okay? Because if they give you a titration curve like this and ask you to find the pH, it's really easy to be like, oh, that's 5. Make sure you go through the process of calculating, right? Because even though it looks like 5 on this curve, and we can even zoom in even more, right? It's right on the crosshairs. But if you calculate it, you actually end up at 5.34. So don't fall into that trap, okay? It's not going to be that easy. But there you go. So you're still within, you're like right at the edge of this buffer zone. And then from here, you begin to see a more dramatic increase in the pH. So just remember that if you're working with a weak acid or a weak base, you're going to have this buffer zone. And if you have the buffer zone, right, where you're working with the pH and you're having an anion or a cation that is hydrolyzing with water, meaning it's reacting with water, you're going to have to use this equation, okay? Or this one, sorry. All right, guys. So that's it for today. Let's gear up, and I'll see you guys tomorrow.